Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The year 79 witnesses a pivotal moment in the unfolding drama of physics, a moment indelibly etched in the annals of scientific thought. It is in this year that Ludwig Boltzmann, a scholar of immense intellect and a profound understanding of the physical world, published his seminal work on the relation between the second law of thermodynamics and probability calculations regarding the states of equilibrium. This paper, a testament to Boltzmann's genius and his courageous exploration of the fundamental nature of reality, represents a bridge between the seemingly deterministic laws of thermodynamics and the probabilistic nature of the microscopic world. It fundamentally reshaped our comprehension of entropy, equilibrium, the very arrow of time. Prior to 1979, the second law of thermodynamics, a cornerstone of 19th century physics, presented a peculiar puzzle. It stated, unequivocally, that in any closed system, entropy, a measure of disorder or randomness, can only either increase or remain constant. It can never decrease. This law seemed absolute, a cosmic decree dictating the inevitable march towards equilibrium. Yet, this law, when confronted with the underlying reality of matter, a world of constantly moving atoms and molecules, presented a challenging paradox. The behavior of these microscopic entities, governed by the laws of mechanics, was, in principle, fully deterministic. Given sufficient information about their initial positions and velocities, their subsequent trajectories could be precisely predicted. This deterministic nature of microscopic physics appeared to clash with the irreversible nature of the second law. How could a law describing increasing disorder emerge from a world apparently governed by order? Boltzmann's work, both before and especially 1879, provided a groundbreaking solution to this apparent contradiction. He proposed a radical idea that the second law, while valid on a macroscopic scale, was not a fundamental, absolute law of nature, but rather a statistical one. Instead of viewing entropy as an absolute measure of disorder, Boltzmann proposed that it was proportional to the logarithm of the number of possible microscopic states, or microstates, that could realize a given macroscopic state, or macrostate. This concept is expressed mathematically as S equals K times the natural logarithm of W, where S is entropy, K is the Boltzmann constant, and W is the number of microstates corresponding to the macrostate. The seemingly simple equation, inscribed on Boltzmann's tombstone, the cornerstone of statistical mechanics, and provides a bridge between the microscopic and macroscopic. To appreciate the revolutionary nature of Boltzmann's insights, it is essential to delve into the details of his argument. Boltzmann began by considering the behavior of gases, systems readily accessible to experimental investigation. He imagined a gas composed of a vast number of identical molecules in constant motion. These molecules, colliding with each other and the containing walls, possessed a range of velocities and positions. The macroscopic state of the gas, its temperature, pressure, volume, could be described by a set of parameters. However, this macroscopic state could be achieved by a multitude of different arrangements of the individual molecules. Boltzmann realized that the most probable macrostate was uncorresponding to the vastest number of possible micros. In a groundbreaking departure from conventional thinking, Boltzmann applied probability calculations to this situation. He argued that if a system is observed over a sufficiently long period, it will spend the overwhelming majority of its time in the macrostate with the highest number of microstates, the state of the maximum entropy. The increase of entropy, as described by the second law, was simply the tendency of a system to evolve towards the most probable state. This perspective provided a profound reinterpretation of irreversibility. The second law was thus, in Boltzmann's view, a consequence of pure chance, a matter of probabilities, not of absolute dictums. Systems do not have to increase entropy, rather, they are overwhelmingly likely to. This insight resolved the paradox of the second law, making it compatible with the underlying reversibility of microscopic. The mathematical tools employed by Boltzmann were as significant as his conceptual breakthroughs. He utilized the concepts of probability distributions, particularly the Maxwell-Boltzmann distribution, to describe the distribution of molecular velocities in a gas. He extended this to analyzing collisions between the molecules. His work relied on meticulous calculations and involved the derivation of complex equations. This work required prodigious mathematical skill, demonstrating a firm grasp of combinatorial analysis, the emerging field of statistical math. The immediate impact of Boltzmann's work was profound. Although its acceptance was far from immediate, it provided a new understanding of the second law and its relationship to the underlying microscopic world. This approach offered a method for calculating thermodynamic properties from the microscopic behavior of matter. One of the most immediate applications was the theoretical calculation of the speed of diffusion and of the viscosity of gases, providing a deeper understanding of these phenomena at the molecular level. This work provided a crucial link between macroscopic observations and the underlying atomistic nature of matter, something that was heavily debated at the time. Calculations showed close agreement with experimental data. The evolution of Boltzmann's ideas and the subsequent use, generalization, and building upon of his work by other scientists contributed to the rapid development of statistical mechanics. The concepts he established opened new avenues in theoretical physics and influenced the development of numerous fields. His statistical approach was extended to other systems, including solids and liquids. It also provided the foundation for the development of quantum statistics in the early 20th century, which was essential for understanding the behavior of systems at the atomic and subatomic levels. The Boltzmann constant, which translates energy into temperature, became a fundamental constant in physics, linking microscopic and macroscopic quantities. The equation S equals K times the natural logarithm of W remains a central pillar. It appears on the walls of physics departments and is a constant presence in the minds of anyone dealing with thermodynamics. The scientific community's response to Boltzmann's work was initially far from universally supportive. His ideas faced strong opposition, primarily from those who adhered to a more traditional, deterministic view of physics. The atomistic interpretation of matter was still subject to debate, with many influential scientists hesitant to fully embrace the idea that all matter was made of individual atoms. In particular, the concept of atoms was not fully accepted at the time. Critics like Ernst Mach argued against the existence of atoms. Moreover, Boltzmann's statistical interpretation of the second law was seen by some as a weakening of the law itself. If entropy increase was merely a matter of probability and not an absolute rule, then the foundations of thermodynamics seemed to be undermined. This resistance to his ideas, coupled with personal tragedies, took a heavy toll on Boltzmann. The lack of recognition and the relentless criticism from his peers contributed to his eventual suicide in 1906. It is a tragic irony that Boltzmann's work, which provided a profound understanding of the statistical nature of the universe, was itself a victim of the statistical fluctuations of human perception and comprehension. Despite the initial resistance, Boltzmann's ideas gradually gained acceptance as experimental evidence mounted in their favor. The work of scientists like Max Planck and Albert Einstein, who used Boltzmann's statistical approach to explain the properties of blackbody radiation and Brownian motion, respectively, provided further validation. Einstein's work on Brownian motion, in particular, provided a conclusive demonstration of the reality of atoms and molecules and confirmed Boltzmann's fundamental insights. The vindication of Boltzmann's statistical approach and the consequent acceptance of the atomic theory was a turning point in the history of physics. The influences on Boltzmann's work were multifaceted. He was deeply influenced by the work of James Clerk Maxwell, who had developed the kinetic theory of gases and introduced the concept of a statistical distribution of molecular velocities. Maxwell's theoretical framework, which used probability to derive the behavior of gases, provided a foundation for Boltzmann's statistical approach. Boltzmann explicitly built on and extended Maxwell's ideas, creating an expanded mathematical description of molecular motion that incorporated the concept of entropy. Another critical influence was the work of Rudolf Clausius, who had formulated the second law of thermodynamics and introduced the concept of entropy. Boltzmann sought to provide a deeper understanding of entropy, explaining it in terms of the microscopic properties of matter. Clausius and Maxwell together formulated the initial groundwork for Boltzmann's developments. The legacy of Boltzmann's work resonates throughout modern physics and beyond. His statistical methods have become indispensable in countless areas, including condensed matter physics, cosmology, and information theory. The concept of entropy is now understood as a fundamental measure of disorder, not only in physical systems but also in information theory and computing. The Boltzmann constant is a fundamental constant of nature, connecting the microscopic and macroscopic worlds. He demonstrated that the second law of thermodynamics does not represent an absolute rule, but a statistical one. Boltzmann established a profound connection between the microscopic and macroscopic worlds, a connection which lies at the heart of modern physics and our understanding of the universe. His work provides an enduring testament to the power of human intellect and the pursuit of knowledge. It serves as a profound reminder that even the most seemingly deterministic laws of nature may have their roots in the statistical dance of the microscopic world.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.